today. So from next week, we're going to be doing analytical geometry. We're going to be looking at circles. But before I get into today's lesson and talk about the very last thing that we're going to cover in trig, I just wanted to bring your attention to the fact that we are going to be offering an exam prep session. It's going to take place on the 14th of May and again on the 21st of May. I'm not 100% sure at what time or how long, but I would imagine that each session would probably be 2 hours in duration. So probably more than likely we would do paper 1 work on the 14th and paper 2 work on the 21st. I'm guessing when I say that, but that's what I would think. And the total for both would be 199 Rand. So if you are interested in attending these sessions, your parents would have been emailed a registration form. So please, would you ask your parents, if you are able to attend and you do want to attend, to fill out the registration form and send it back to Watobe. And yeah, we're going to try and sort of keep the classes small, so space is limited, so that we can best help whoever is going to be attending. Okay, so that's just the one thing I wanted to inform you about today. Yeah, both Saturdays. Yes, Nicole, that's quite right. Okay, so let's go on and let's talk about today's lesson. So today we're going to be talking about equations and general solutions. And I don't know if you've been keeping track of what I've had at the top, but we haven't had calculators this entire time. And now is the very first time we're actually allowed to pick up a calculator. And that is because when we are solving a trig equation, they are asking us to determine a value of theta. So they're asking us to solve for an angle. So this is the first and only time in trig where we are now allowed to use calculators. So last year, you were introduced to the idea of general solutions. You didn't do it in grade 10, but you did do general solutions in grade 11. And before I get into general solutions again, I think it's really important, and that's why I always try and start my lessons in the same way. Like if there was somebody, like maybe your mum or your aunt or someone, and they said to you, explain to me what a general solution is, would you be able to tell them? Would you be able to tell them exactly what it is that you're trying to calculate? So I'm putting that question to you now quickly. You can answer me in the chat. If you had to explain to your mom what a general solution is, would you be able to do it? Yes or no?
No, ma'am.
No, thank you, Tatso. Oh, very funny, Nicole. Harriet says no. Cool. Boy Sherpo says no. Lovely. I'm so glad all these are no's. Does everybody else say yes? All right. So I'm glad that there are, thank you, Maite, thank you, Ryle, that there are a few of you that have said no. Yeah, where would you start? So I'm going to show you where I'm going to start, Adam. And I'm hoping that by the time we get to the end of this hour, to be honest with you, an hour is not nearly enough. I mean, I could sit here for 6 days and talk about general solutions and equations and whatever. But that's the problem with CAPS. It's not the problem with you guys. All right, so a general solution, or understanding what a general solution is linked to the idea of graphs. Okay, so just like a parabola is a function and a straight line is a function and a hyperbola is a function, so you get your trigonometric functions as well. Okay, so the one that I have here that I've sketched for you is the graph of y equals sine x. Now, if I'm talking about a parabola, so let's say something takes the form y equals x squared minus 7x plus 12. What does y represent? What's another word for y? Output? Yeah, f of x, correct, Kumo, all right? But it's output, isn't it? All right, so in other words, a number goes in, the rule is used to generate a sequence of numbers. Okay, so y is what we get out, x is our input. That's what goes in. Everybody happy with that? It's exactly the same thing with the sine function as well, except that the x's that are going in are your angles, but it's still on the x-axis. So here where I've got 0 and 150 and 300 and 450 and 600, those are degrees. Okay, so it's 150 degrees, 300 degrees, 450 degrees. Okay, so the x-axis is measuring degrees. The y-axis is still representing output. Okay, so angles are going in and ratios or values are coming out. So let's think about a super simple example that you guys know really, really well. All right. Sine theta is equal to 1 over 2. All right. In this situation over here, I don't know what the value of theta, my input, my x is, but I know the output is a half. So what this means is that somewhere between 0 and 1 on the y-axis lies the value of a half. So if I draw the line y equals a half across here, because this is where y is equal to a half, right? I can read off different values for x. Does that make sense to you? And I can do that where angles are positive, and I can do it where angles are negative. All right, so I could also go and read off over here and over there, and again over here where angles are really tiny, and again over there. I could read off all these different values, these different answers of x or theta when y is equal to a half. How are we feeling so far? Is this making sense? Thumbs up?
Yes, ma'am. Yes, ma'am.
Are we all good? Okay, all right, cool, cool. Cassandra, just bear with me, okay? I just want you to hear me out, because if you understand this, what you're doing when it comes to a general solution is going to make so much more sense, okay? Fine. When you are working with a general solution, what you are doing is you are trying to develop a formula that allows you to work outside of the Cartesian plane, so that we don't have to end up drawing a graph like this and reading off all these values every single time. It allows us to do it algebraically, right? So if we want to work out what our reference angle, or PAA, depends what your teacher calls it at school. Some of them call it a reference angle. Come on, pen. We at my school, we refer to it as a PAA, which means it's a positive acute angle. What you would end up doing, and you can do this on your calculator, is we want to work out what the input is when the output is a half. So to do that, you have to go shift sign on your calculator, put in the 0.5. What comes out?
30.
You get 30 degrees out. Okay, because your calculator is programmed to give you an acute angle. That's why you get 30 degrees out, because the calculator is programmed to give you an acute angle. The calculator is not clever enough to be able to present all of the solutions to you. So it just gives you the smallest answer, okay, or smallest positive answer that is possible. So now we're looking at this and we're saying to ourselves, okay, sine theta is equal to 1/2, all right? Up to here, let me just highlight this in different colors for you, all right? But here is quadrant number 1. Let's just get rid of this line. So I've actually got another diagram where I've drawn. So now here, if you look at this diagram here, it's exactly the same as the one that we've just been working on, right? What I've done in blue though, is that is the line y equals 1/2. So it's exactly the same diagram, all right? So our function that we're dealing with is the graph y equals sine theta, okay? So remember we said that sine theta was equal to 1/2. That half is y, it is the output. It's this value over here, okay? When I look at this value and I calculate my reference angle or my PAA, I end up with 30 degrees. When I look at the graph matrix, all right, here is quadrant number 1. Okay, quadrant number 1 starts at 0 degrees and it ends at 90. Quadrant 2 starts at 90 and it ends at 180, which is over here. There's 180. Quadrant 3 starts at 180 and ends at 270. And quadrant 4 starts at 270 and ends at 360 degrees. Okay. If you have a look at the sine function, okay, can you see that here I'm doing quadrant number 1 in yellow. There's quadrant 1. Can you see that the red line is above the x-axis? That's why sine is positive in quadrant number 1. Okay, here's quadrant 2. And look, the red line is still above. Here's quadrant 2 now. The red line is still above the x-axis. Can you see that? There's quadrant 2. That's why sine is positive in quadrant 1 and quadrant 2. Look here, here's quadrant 3. What happens to the red line? It goes below the x-axis. That's why sine theta is negative in quadrant 3. So what that means when we say sine theta is negative in quadrant 3, it means if we read off any value for y, it's going to be a negative value because it's below 0. That's what it means. Okay, and same story with quadrant number 4. Sine theta is negative in quadrant 4 because the graph is below the x-axis at that point. Okay, we know that the graph repeats itself every 360 degrees. So from when I started here at 0 to when I got there, that was a revolution, one revolution. Okay, one revolution. If I then start at this second orange point and I do another revolution, I'm going to end up here. Okay, so this is where there's been one revolution. Over here, I've now done 2 revolutions or 2 turns around the origin. I hope this is making sense. If I now want to go back the other way, all right, this is where k would be equal to -1, which would allow me to cycle once backwards. Or if k was equal to -2, it would allow me to cycle a second time going backwards. Now I'm going to talk about what the k means now. Just bear with me for a moment, okay? So you write down sine theta equals 1/2. You calculate that the RA, the reference angle, is 30 degrees, okay? So that means that we are reading off 30 degrees here. This is 30 degrees there. But this is not the only place where it's equal to 30 degrees, because sine theta equals 1/2 means that we can find a solution in quadrant 1 where theta is equal to 30 degrees. But we can also find a solution in quadrant 2 using our reduction formulae. What is the reduction formula for quadrant 2, Matrix?
180 minus theta.
Exactly. So 180 minus our reference angle, that gives us 150. So can you see what we have done is we have cycled forwards to 180 here. And then we have changed direction and gone 30 degrees backwards. And that's where the 150 comes from. Does that make sense?
Yes, ma'am.
Okay, remember this is about direction. So when I go in this direction, angles are positive. When I go in that direction, angles are negative. Now, I have a solution every cycle of 360 degrees. So where I drew in purple over here, that is where I can read off 1. But where is the graph going to be repeating itself again exactly 360 degrees later? Here. And that's why I'm going to get another solution there. Does that make sense to you? Okay, or with the green one. If I'm going to read off over here, exactly 360 degrees later is this point over here, which means that I can read off another solution over here if I need to. Okay, that is the purpose of the general solution. All right, so it is a way of allowing us to find these solutions algebraically instead of us always having to now draw a graph. All right, what it allows us to do is it allows us to cycle forward, because remember k is an integer. So it allows us to cycle forward when k is 1, k is 2, k is 3, k is 4. And it allows us to cycle backwards when k is -1 and -2 and -3, depending where on the x-axis we want to try and find a solution. So a general solution is a formula that you make that allows you to find solutions anywhere on the x-axis. Does that make sense?
Yes, ma'am.
Okay. Thank you, Emitle. I don't know how everybody else is feeling, but this is the idea. This is the idea behind it. Let's go and have a look at a typical sort of question that they would expect you to be able to do in matric. Okay. All right. Oh, that's the other thing. How do you know when you're supposed to do a general solution? There are 3 situations. Okay. Number 1, you're told to. Number 2, you're asked to solve outside, and you will always be asked to solve outside the domain 360. And number 3, if the angle that they ask you to solve for and the angle that they give you are different. So let's say if they say to you, solve for x if sine 2x equals 0.81, let's say. Okay, then the angle they're asking you to solve for, 2x, is different sorry, the angle x that they're asking you to solve for is different to the angle that is given, which is 2x. That's when you know that you need to do a general solution. Okay, so sometimes they will ask you to just do the general solution. Sometimes they will ask you to do the general solution and then use it to find answers in a certain place on the Cartesian plane, like they are here in blue. Now, what you need to recognize when you look at example number 14, what do you see on the left-hand side? What is this thing here? You know these now. You've been learning about them for a while that I've just highlighted in purple. What's that called?
A cos compound angle.
Cos compound angle. All right. And when it's expanded like that, we have to do the reversal of the expansion. Remember, when it looks exactly like one of our compound angle formulae, it's like a key fitting into a lock. We can now go back the other way. So we've got cos, 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 sine, sine. This is a cosine compound angle. And if you remember, cosine compound angles don't keep their sign. So this is going to become cos theta minus 24 degrees equals 0,715. Does that make sense to everybody? Okay. So you are now at this desirable situation where you have the sine, the cos, the tan of an angle equals a ratio. When you get there, that is when you are meant to find your RA or your PAA. So I like to call it a PAA for positive acute angle. I'll just write that on the side so that you remember. Positive acute angle. And that means that we always ignore the sign of our ratio when calculating the PAA. We use the sign of our ratio when we determine which quadrants we work in. Right? So now on your calculators, you are going to go shift cos. Pop in the 0,715. And out comes a number. That is your PAA, your reference angle. Because we are going to be combining it with 180, 360, we can round it off at this point, okay, because our decimals are not going to change. So I don't know about you guys, but I'm getting 44,36 degrees. Whatever you do, make sure your calculator is on degrees and not on radians. Otherwise, you're going to get funky answers. Okay, so be very, very careful with trig. Make sure that your answer is on, your calculator is on degrees. So in terms of our cos graph, what we've done here is we've now identified a ratio, a place where it's equal to 44.36. Okay, so in other words, somewhere along the graph, okay, your cos graph looks something like that. If this is 1 over here, then 0,715, I guess, is going to be somewhere over there. It's pretty close to 1, isn't it? Right, so we've come over here, we've come down, and there is our 44,36 degrees, our input when our output is 0,715. Okay, but they want us to solve over here, so it's going to be somewhere negative up to 90. So between here and here, we want to find out how many solutions there are and what their values are in this particular case. All right, so that's how it relates back to the graph. This ratio that I'm highlighting in pink is positive. So what that means, if we think about our cast diagram, where is cos positive? Cos theta is positive in quadrant 4 and quadrant 1. So that means we need to do a solution in quadrant 4 and quadrant 1. In quadrant 1, we are using our angle theta, so this is for quadrant 1. Theta minus 24 degrees is our angle, is equal to our PAA plus multiples of 360, because that is how often the graph is going to repeat itself. What I need to do now is simplify. So in other words, I need to add 24 degrees to both sides of my equation. That's going to give me an answer of theta equals 68, 6 degrees plus k times 360. And I mustn't forget to put in here that k is an element of the integers. I don't actually have to write it on every line, but I do have to write it once. Cos theta is also positive in quadrant 4. So now for quadrant 4, my angle is theta minus 24 degrees is equal to, in quadrant 4, my reduction formula is 360 minus my PAA plus multiples of 360 degrees, because cos graphs repeat themselves every 360 degrees like sine graphs do. Now, again, solving for theta, I'm going to take 360, I'm going to take away the 44.36, and I'm going to add 24 to my answer, and that gives me 339.64 degrees plus k times 360. How's everybody feeling at this point? Like a thumbs up or a thumbs down? Amazing.
Yes, ma'am. Because my
Really?
teacher never really taught me the general solution like this. I never thought you could use the quadrants like the 180 degrees minus to get your answers properly. She normally gives us a formula and says this is what you should learn. So this is quite helpful.
I'm so glad, because you see, the thing is, Tatsu, I want you to understand what you are doing, because it's only when you understand what you are doing that it's going to be of any use to you. You can't apply knowledge or something to a situation that you don't understand. It's useless to you if you don't understand it. So that's why, for me, starting here is the most important thing. And I really do hope that it is making sense to you in the way that I am intending it to be. Okay.
Thank you.
It's a pleasure, Tatsu. It's an absolute pleasure. So it says you've got a question. Kumo's got a question, ma'am. Because of theta being an element of minus 90 to 90, will the answer of quadrant 4 be applicable? It depends on the value of k, Kumo, because remember, k is an integer. So this is where the k part comes in. So when k is 1, it allows us to cycle one turn of 360 degrees forwards. When k is 2, we cycle another turn of 360 degrees forwards, etc., etc. We can go forwards and we can go backwards as well. So now, when we want to try and find solutions between negative 90 and 90, the best thing for you to do, all right, is, because you don't have to show how you got the answers. When you put the solution onto your calculator, put it in like this. So let's do the 339.64 first. Okay, so in your calculator, you're going to do this. You're going to go 339.64 plus 360. Now you're going to use brackets or press times, right? Now, Kumo, if I put in 0, my answer is going to be 339.65. It's way too big, right? So 0 is too big. If the integer 0 is too big, what is the next smallest integer? -1, isn't it? So let's put in -1. We're going to times 360 by -1. What do we get as an answer? I hope you're getting the same. Yeah?
Negative 20,36.
There we go. All right, negative 20, I'm getting 3.5. Am I doing something wrong here? Oh, sorry. I pressed 0.65. Sorry, hang on. It's a bit silly of me. 4. Sorry, yeah, quite right, 3, 6. Thank you. So can you see, Kumo, we do get a solution from this. Okay, it depends on what the value of k is. Right. Now, if you leave the k at the end, it means that you don't have to go back and retype the whole thing into the calculator. So let's say we just want to make 100% sure, positive, that we're not missing anything. We're going to go back on our calculator and we're going to change the -1 to the next smallest number, which is -2. And we're going to press equals. What do we get now? Minus 380. Yeah, absolutely. Is that useful to us in this situation?
No, ma'am.
So now we stop. We stop. Now let's go to the other formula. Again, put in the 68.36 plus, put the 360 first and now times. Okay. If we times by 0, what are we going to get as an answer, Matrix? We're going to get 68.36, isn't it? Right? If we times by 1, which is the next biggest number, we end up with 428.36, too big. Okay, so let's go back and check that -1 doesn't give us something that we can use as well, but I don't think it's going to. No, it's -291.64. So that's it. These are the only 2 solutions possible. And that factor of k is what allows us to move forwards and backwards. Do you feel like you understand this a little bit better now? I hope.
Don't you indicate that you used k? I mean, don't you indicate k equals -1? You
don't have to do that, Tandlewethu. You don't have to show the value of k for the solution that you have obtained. It's not necessary. So in this situation over here, where would your marks be allocated? Okay, well, first of all, was using your compound angle. Sometimes they give a mark for the PAA, sometimes they don't. Definitely going to be on our general solutions. There's usually a separate mark for writing k as an element of the integers, and then probably on both solutions. 1, 2, 3, 4, 5, 6. Might be a little bit much for this particular question. Maybe there wouldn't be a mark for the PAA here, but you do not have to write what k is equal to for your solutions. The only other thing I should have done here is I should have written the word or. Okay, so you can either make a list of your solutions, like using set notation. If you do that, then you're supposed to write theta as an element of, and then put the most negative number here. Oopsie, that's not supposed to be a semicolon, 36 degrees like that. Then the semicolon, and then 68.36, like that. Okay, so either or. I always just do it the first way rather than making a list. Okay, are you ready to move on?
Yes, ma'am.
Okay, so if you do want to come back and try one like this yourselves, okay, I have chosen this one over here. So if you do want to come back and watch the video again at a later stage, we can do that. What I'm going to do now, if it's all right with you, is I'm just worried about time here. I want to talk about questions like this, okay, because this is a far more likely scenario. I have never seen in a final paper, and just because I haven't seen it doesn't mean that it can't be there, but I have never seen them use a compound angle in a final paper for a general solution. It's normally some kind of factorizing that's involved. Okay, so if we have a look at the examples that I've got here, Tatsuo, why don't you choose one? Do you want to do A or B or C? Which one?
Ma'am, B. B looks interesting.
Okay, let's do B then. Perfect. All right. So what all of these have in common is that you have to factorize. It's a pleasure, Mpile. You have to factorize. Okay, so you don't know what sine alpha equals. All right, so you have to factorize in this situation. And that's where those hints that I was giving you last week also come into play. So in other words, you remember when I was saying to you, what do you see the cos 2 alpha with? Okay, if you see cos 2 alpha with cos alpha, rewrite cos 2 alpha as 2 cos squared alpha minus 1. All right, now in this example that Tatsuo has chosen, all right, we don't have to worry about cos 2 alpha. We've got 2 sine squared alpha plus sine alpha minus 3 equals 0. It is now in standard form. From an algebraic point of view, it is identical to something like 2x squared plus x minus 3 equals 0. Identical. So if you were asked to solve the question on the right, you would factorize. You'd have 2x in one bracket, x in the other bracket, 3 in one. Is that going to work? Yes, it will. If that's a plus, then that's a minus. Let's just double check that I've done this correctly. So 2x squared minus 2x plus 3x gives us the plus 3 in the middle. Absolutely. Now you've applied your zero factor law, right? So now you've got x equals negative 3 over 2, isn't it? Or x is equal to 1. It is exactly the same idea here. So you are now factorizing 2 sine alpha times sine alpha equals 0. Here's your plus 3. Here's your minus 1. Either sine alpha equals negative 3 over 2 or sine alpha equals 1. Do you see the similarities between the two? That's what you're doing, okay? You can, but when you are factorizing by taking out a highest common factor, Kumo, then sine theta has to be in every term. So if we were doing question number 1, you'd have to factorize by taking out a highest common factor. But question B is a trinomial. Okay, so you have to factorize it as a trinomial. But question A, you could take out a highest common factor because you would have written it as 2 sine alpha cos alpha, that's your sine 2 alpha, plus 2 sine alpha equals 0. And then you could have taken out 2 sine alpha, whoopsie, I need to write the bracket there. You could take out 2 sine alpha as a highest common factor, and then you'd end up with cos alpha plus 1 equals 0. Okay, does that make sense? Cool. So yeah, where you have to apply the correct kind of factorizing. If it's a trinomial, factorize it like a trinomial. If it's highest common factor, take out a highest common factor. If it's difference of 2 squares, factorize difference of 2 squares. So just be
Can you
aware
still
of,
use the formula?
Absolutely.
Okay.
Absolutely, you can use the quadratic formula in order to be able to work out what your ratios are. Okay, so now remember, these are ratios. These are outputs. Okay, so if we now go back to our graph and we go and try and find a place in the graph, remember minus 3 over 2, this is equal to minus 1.5, isn't it? Now let's go back to our graph wherever I had it. No, not that. Where was it? It was over here somewhere. There we go. Okay. All right. Here's minus 1. So minus 1.5 is here. So again, if I draw a horizontal line everywhere where y is equal to minus 3 over 2, are we intersecting our function? Is the orange line crossing the red line anywhere? No, it's not. It's not. And that's why if you are working with the sine function, if your ratio is bigger than 1, bigger than 1 or smaller than -1, there are no real solutions. Okay, there can only be real solutions between -1 and 1. Can you see that? That is the range of your function. And the cos function is exactly the same. It ranges between -1 and 1. So it's not possible to find solutions. So what you would do, and I chose this example on purpose because I wanted to talk about what we're discussing now. When you get something like this, so it's sine or cos theta that is greater than 1 or smaller than -1, you write here no solution. Okay, and now what we are going to do is we are only going to concern ourselves with sine theta being equal to 1. Okay, so again, we're going to work out our RA or our PAA. Shift sign, put in the 1, what comes out? 90. We're going to use the K method now. We're not there yet. Okay, we're going to use the K method. Where to remember, we put the K into our general solution. So first we have to factorize, then we find our PAA. All right, so number 1, you are factorizing. Number 2, PAA. Number 3, all right, you are now in number 3, we're going to do our general solutions. We're going to write our general solutions based on quadrants. Okay, and remember which quadrant we work in is the sign of our output, the sign of our ratio. So 1 is positive. So here, matrix, we are doing a solution in quadrant 1 and in quadrant 2. Now, something interesting happens here. In quadrant number 1, our angle alpha is equal to our PAA plus multiples, sorry, that's supposed to be a K, of 360. Right? That cannot be simplified any more than it is. Look at what happens in quadrant 2. Okay, for quadrant 2, we use 180 minus. Can you see we get exactly the same answer? Okay, so you don't have to repeat yourself. If you've already got this as a solution, you don't then have to go and repeat it here and then go and repeat it here. Okay, repetition is not required. It's like if you solve a trinomial like this. So if I solve x squared minus 6x plus 9 equals 0, right? I have equal roots. So x minus 3 times x minus 3 equals 0. All I have to do is say x equals 3. I don't have to say x equals 3 or x equals 3. It's the same idea. Okay, so you don't have to repeat yourself. All right, and then remember that factor of k that's there, this value of k here. This is what allows us to then cycle forwards or backwards and find solutions. So here, all they asked us to do was determine the general solution. So we're stopping here. Okay. No, Kulani, because remember, there are always going to be 2 places where each ratio, each function will be positive or negative. Okay, so the only reason that we're working with quadrant 1 here is because quadrant 2 gave us the same solution. Okay, so no. Right, both solutions are valid, but in this case, they are identical, which means we only need to write our answer once. We don't have to repeat ourselves. If our solutions are different, then we've got to write both of them, like in this example over here. Okay, these 2 solutions were different. So I have to write both of them because they're going to generate different answers. Okay, so that one and this one over here were different. I'm highlighting it in sort of a light gray color. So I have to write both of them. All right, whereas here, they're the same. Okay, so I don't have to write both. Does that answer that question? Okay. Cool. All right, so I'm trying to, it's a pleasure. I'm trying to show you where possible how much trig is like the algebra that we know and we learn, and that just kind of makes it a little bit easier to understand as well. Okay, so now we've got 15 minutes left, my lovelies. Let's have a look at these questions over here, and I'm going to ask Cassandra. So I actually haven't given, hang on, Cassandra, I haven't given the boys a chance. Let me ask. Okay, Emihle, pick one. Emihle? Okay, so Emihle is not talking. Cassandra, are you there?
Can you please do E?
You want to do E? No problem. Fine, let's do E then. Okay, so Cassandra says let's do E. Good, I like it, Cassandra. I'm glad that you were ambitious. All right, so we've got 3 sine squared theta plus 2 sine 2 theta. Now be very careful how you write, okay? This 2 over here is a square. This 2 over here is not a square, it's a coefficient. Be very careful. Often with matrix, the square and the 2 kind of end up as 1, and we don't know whether we're talking about sine 2 theta or sine squared theta. Be very, very careful how you write things. Okay, plus cos squared theta equals 0. Okay, so the first thing that we need to do is work with our sine double angle. So we're going to expand 3 sine squared theta plus 2 times 2 sine theta cos theta plus cos squared theta equals 0. So in other words, what we've really got here, matrix, is 3 sine squared theta plus 4 sine theta cos theta plus cos squared theta equals 0. Oh, shame. Sorry, Mark. If you're here in our next lesson, I promise you, Mark, I will let you choose first. Okay. All right. So now we have to factorize. We have to factorize. Cool. All right. This is a trinomial, right? If we were doing this in an algebraic sense, this is what it would look like. Okay. So for example, if they asked us to factorize something like 3x squared plus 4xy plus y squared equals 0. That's what it's the equivalent of. Okay, so in this case, the sine theta and the cos theta are used as 2 different variables. Okay, and you're going to see what happens with this particular question, right? So if we were working in pink, we would factorize and we would put 3x in one bracket and 1x in another bracket, and then we'd have our 0. And to get y squared at the end, we'd need a y here and a y there, wouldn't we? Because the middle term and the last term are both positive, the only thing we can do is have a plus here and have a plus there. So we've got 3x squared, 3xy plus 1xy gives us the 4xy in the middle, and positive y times positive y gives us the y squared at the end. So that's what we've got here. So now when we write it with trig, we've got 3 sine theta plus cos theta, sine theta plus cos theta equals 0. Does that make sense to everybody?
Yes, ma'am.
Cool beans.
Yes,
Now, cool. Now, what's going to happen here? 3 sine theta will be equal to negative cos theta, or sine theta will be equal to negative cos theta. You are allowed to divide sine theta by cos theta because sine theta divided by cos theta is an identity. You cannot divide cos theta by sine theta. You cannot divide sine theta by tan theta. You cannot divide tan theta by sine theta. You can only divide sine theta by cos theta because it is an identity. All right, so now we are dividing both sides by cos theta. This gives us 3 tan theta equals -1. Whoopsie, forgot the theta. And therefore tan theta is equal to -1/3. On this side, we're also allowed to divide by cos theta. And this gives us tan theta is equal to -1. Okay, I'm so glad you picked this question, Cassandra. Right? Whoever would have thought that we started with sine theta and cos theta, and now look at this, we're actually doing a solution for tan theta. Now, unfortunately, I didn't get to show you a picture of the tan function. But tan is different because it's y over x. So whilst there are asymptotes, there is no restriction on what the ratio can be because it's not a curve that repeats itself like this. It goes up forever and it goes down forever. Again, once we have got to this situation, tan theta, sine theta, cos theta equals a ratio, we are now ready to find our PAA. So let's do the tan theta equals -1/3 first, okay? So now we're going to find our PAA. Remember, we are going to press Shift tan, and then we're going to put in +1/3, not negative. The negative is there to tell us which quadrants we're going to work in, okay? So Shift tan, 1 divided by 3, and that gives us a PAA. I'm getting 18,43 degrees. Tan theta is negative in quadrant 2 and quadrant 4. Right. But again, what you're going to have here is a rule that the one rule will allow you to calculate everything that the other rule will. But I'll explain what I mean by that quickly. Let's just get them down. Okay, so our angle theta is equal to, in quadrant 2, 180 minus 18,43 degrees plus, now here, k times 180. Okay, that is because tan graphs repeat themselves every 180 degrees, not every 360 degrees. Okay, so sine and cos graphs repeat themselves every 360 degrees. Tan graphs repeat itself every 180. All right, so now we're going to work out what our answer is. We're going to take 18.43 away from 180, and that leaves us with an angle of 161,5. 7 degrees plus k times 180. K is an element of the integers. Okay. Quadrant 4, theta is equal to 360 degrees minus, because that's our reduction formula for quadrant 4, 360 degrees minus 18,43 plus k times 180. K is an element of the integers. Okay, hopefully you guys are also getting 341,57 degrees plus k times 180. K is an element of the integers. I so wish that I had another 3 or 4 lessons with you to explain what it is that I wanted to say. There's something that I'm not telling you, but it's because we're running out of time and it requires a fair bit of explanation. So I'm not gonna say it. But anyway, we'll just leave our solutions like that for now. That's fine. This will get you the right answers. As far as the one on the right hand side is concerned, so here again, let's do this one in orange. Okay, if we go shift 10 and we put in 1, what do we get? We get 45 degrees, exactly. So that means that in this situation over here, our PAA is 45 degrees. Again, tan theta is negative, so that means that we need to do a solution in quadrant 2 and quadrant 4. So in quadrant 2, theta will be equal to 180 minus 45 plus k times 180. K is an element of the integers. Okay, so that leaves us with 135. And just double checking, been a long day. K times 180, KZ, or in quadrant 4 again, so that would be 360 degrees minus 45 plus k times 180. K is an element of the integers. Okay, so that would leave us with 335. No, 315. Okay. So tonight is also quiz night. Before you go off to do the quiz, are there any questions that you want to ask me? Is there anything that I can explain before you go? You sure? You got nothing you want to ask me?
Ma'am,
Yes.
if we were to calculate K, the domain, we have to calculate all 4 answers, get
Yeah, now you see now, Tatso, this is what we need a whole nother hour to sit and talk
4.
about.
Okay.
Okay, this is what we need a whole nother hour, because with the tan function, there's something different. But what I'm going to say to you now, because I don't have the time to explain this to you, is yes, use all 4. Okay, that's not the whole story. You actually don't need to use all 4, but because we've now run out of time, I'm just going to leave it and say, yes, use all 4. What I do want to point out though, before we go, oh God, this, like I said, I could sit here forever with you guys. I just want to show you one thing, all right? If I draw, oh gosh, what is that? Sorry guys, that looks terrible, okay? Remember that we start measuring from 0 here, and we get 90 is over here, and 180 is over here, and 270 is over there, okay? So halfway between 90 and 180 is 135, isn't it? Yeah, 90 plus 45 is 135. Okay. So if our terminal arm, There we go. So if our terminal arm, that's exactly what I wanted. If our terminal arm was anchored here at the origin, and now it goes 135 degrees in that direction, it's going to end up over here, dead bang in the middle. That's going to be at 135 degrees. Okay. Now, if I make a revolution of 180 degrees, where am I going to end up? Is the green line going to move down towards the 180 and the 270, or is it going to go back in the same direction? Where's it going to go?
Back, isn't it going to make a revolution?
Okay, but remember, it makes a revolution of 180 degrees, okay? Because it repeats itself every 180 degrees. So where is it going to end up? Slap bang over here. What's halfway in between 270 and 360?
90.
No, between 270 and 360? So halfway between 270 and 360 is 315. Okay, so in other words, what I'm trying to get at here is that every solution that you can come across using this one, you're going to pick up these solutions anyway. But as I say, that's a conversation for another day, unfortunately. Let's leave it there. You guys have to go and do the quiz now. Yeah, the 3 reasons when we do a general solution. Okay, so let me just go up here. There you go. So there's the 3 reasons when we do a general solution. So when you're told to, when you're asked to solve outside the Cartesian plane, so they give you a domain that you need to solve in. And if the angle that you're solving for and the angle that's been given are different, then you do a general solution. Okay, Matrix. It's a pleasure. Okay, everybody. Yeah, thank you so much for joining us. And yeah, remember to register if you want to join the exam prep sessions on 14 and 21 May. And Nicole has kindly posted the quiz link in the chat. Take care, everybody. Thank you. Bye. Pleasure to be there. Bye, Maite.
Bye,
Bye,
ma'am.
Sandra. Bye, Tatsu. It's a pleasure, Kanisile. It's a pleasure, Liam. I hope it was useful. Oh, good. I'm glad. Oh, thank you, Liam. Thank you. That's what I want, you know, is just to be able to make things easier for you guys. So that's great. Thank you. Is there anybody else who wanted to ask a question who's still here? Sam Kelisiwe, Ryle, Maite, Letu, Kanisile, Bochepo. So I put them in the waiting room because they're not answering.
Okay. Yeah. I think they've all left.
I think they've all left and they just forgot to log out or whatever the case was. Okay, I hope I do make sense, Nicole.
Yeah, no, honestly, Lee, you're really, like, as a teacher, you're exceptional, really, you are.
Oh no, that's not.
No, really, honestly, I've been through the hundreds of maths lessons, and like the way you did the graph at the beginning, I think even I was like, wow, yeah, that makes a lot of sense now.
Oh,
Like
I'm so glad, because I mean the thing is, how can you apply any of this if you don't actually understand what it is that you're doing?
Yeah.
You have to
Yeah.
understand what it is that you're doing. So
Yeah.
okay. Oh well, I'm glad it did make sense, because I was like,
Thank you.
don't I? Because I always do this at school, and I was like, I wasn't sure whether this was going to be the right platform and whether I was going to get it across in the way that I wanted to say it. And you know, we're chasing against the time here as well, but I think for a lot of them it made a difference. So
Yeah,
or for a few
definitely
anyway.
Yeah, it paid out the time in the beginning, because then afterwards the questions, then the
You
kids
just zip through it, don't you?
Yeah.
Yeah, exactly.
Yeah.
Exactly. That's the whole idea.
I think
All
they
right.
got it, most of
I
them.
hope so. I hope so. But anyway, that's it. That's trig done. But yeah, thank you very much. It's always just nice to hear. You know, I'm always happy for people to tell me what they think and if I can do something better or differently or whatever.
Yeah, good. Just keep doing what you're doing, Lee.
Okay. All right. Thank you so much for all your help and your assistance. You're always so positive and you've got a really nice way that you talk to them and you keep encouraging them in the chat. So I really appreciate that. Thank you so much for your support. Okay. All right.
Enjoy your weekend. I'll see you on Tuesday then.
Yes, awesome. Okay, take care, Nicole.
You too, Lee.
Okay,
Bye.
thank you. Bye.